Okay, so we want to continue our discussion of general functions. We're going to whiz through some stuff, all the topics. Let's see. I believe we kind of just ended it with a general discussion of what functions are. And that in the real world setting, we kind of think of any function as something we measure. In particular, it's going to be a little more specific on that. It's going to be something we measure against another variable. We need at least two variables for functions, but usually we're measuring some value of an object or a system, and that value is going to change with regards to another variable, often time. If we expect a system to evolve over time, then time is usually our independent variable. The thing we want to measure that is changing over time is going to be our function, or we're going to be able to model that thing we're measuring as a function. Likewise, if we have any sort of particular dimensions, if say a radius changes in the system, we can measure area, we can measure volume. Both of those are going to change with regard to the radius, and how they change based on whatever geometric shape we have. We can model that with an equation, which ends up being a function. So today we're going to just whiz through all the properties of functions, the caveats of functions, the types of functions, and we will see at the end if we have any time for examples, we can do some examples. So we gave formal definitions of what a function was. The specific terminology, hopefully everyone has seen in terms of the independent and dependent variable, the sets of which those variables are going to span are going to be the domain and range. So the domain is the set of all possible values of the independent variable. And the range is going to be the set of all possible values of the dependent variable. The types of functions we're mostly going to be working with in this class. There's kind of a bunch of building blocks of functions, and we're going to apply and modify different transformations of these functions. So let's whiz through the types of functions that we're going to commonly see throughout the rest of your mathematical and STEM careers, and sort of increasing in order of complexity. So first functions we usually start to see are linear functions.
Sorry, man.
Hopefully everyone's familiar with linear functions. The key equations with this, we're going to model linear functions as either y equals mx plus b, gives us our slope-intercept form, or y minus y1 equals m times the quantity x minus x1 is going to be our point slope form, also very useful. And we will use that later this semester once we get into tangent lines and finding the specific lines relating to other functions at specific points. When we build up from linear functions, we have polynomial functions. These are going to be functions of the form, all right, f of x is equal to an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a naught. So n is going to be an integer in this case. The a sub n's are just going to be constant. So they're just going to be any real numbers. Common examples, we see quadratic functions. But we don't always have to have nice integer values for the coefficients or even rational values. Again, the coefficients can be any real numbers. So we could have like pi x to the 4th minus root 2 x cubed plus 17 over 31 x squared minus 400x. The next type of function we get into are power functions. These are going to be functions of the form x to the a for some real number a. Whereas here, polynomials, the exponents for polynomial functions are all going to be whole numbers. For power functions, we start to vary these whole numbers. And so when we take a look at the different values of a, we get different concepts arise. So, for example, we can have f of x is equal to x to the 1/2. And so we commonly think about this that, so for f of x being a power function x to the a, if a is equal to 1 over n, where n is an integer, then this corresponds to the nth root of x. So our x to the 1/2 corresponds to the square root of x. X to the 1/3, cube root of x, etc. And then we can combine this concept with our power functions or with our polynomials. So if we have f of x, or let's use g of x, is equal to...
Mr. Belcher,
Yes.
it's cutting out pretty bad. The video's just frozen.
All right, so there might be a little jump on the video here. We had some lag issues that we wanted to settle. So let's go back over this discussion of power functions. And again, let me know if it starts to lag out. So we're discussing power functions where now the exponents of x are any real numbers. And so how do we think of these? We want to think of these first starting off as fractions. And so our example we started with was x to the 1/2. And if we have something like x to the 1/2, or in general, if we have a power function x to the a, where a is some 1 over n, then we want to think of f of x as the nth root of x. And so our x to the 1/2 is the same as square root of x. X to the 1/3, cube root of x. in general, if we have more complicated fractions, we can combine this with polynomials. So if I have something like x to the 3/4, by basic algebra, this is the same as x cubed to the 1/4. In other words, this is going to be the 4th root of x cubed. But our powers don't always have to be rational numbers. It's really nice when they are, and often pretty much all situations you're going to see any complicated exponents, they're almost always rational numbers. But we could have functions like x to the pi. However we want to make sense of that, a little bit beyond the scope of the course, we can think of it as maybe a limit of certain rational functions or rational exponents. But again, most often we're not going to see examples like this. The next level that we kind of get into with these power functions so for f of x equals x to the a, if a is less than 0, in other words, if a is negative, then we get what's called the reciprocal function. So more concrete examples, when we have f of x equal to, most commonly, or I guess most basic example, x to the -1, we simply mean that's the same as 1 over x. So f of x is 1 over x. So careful with that. Always remember, a fractional exponent means a root. Negative exponent means a rational expression or a fraction of the entire function. So a little more complicated examples, we can combine all of these concepts. If we have something like g of x is equal to x to the -2/3, using our basic algebra properties of exponents, however we want to approach this, we can think of this as x to the 2/3 to the -1, or we could flip that and have x to the -1 raised to the 2/3. We could have it as x squared to the 1/3 to the -1. The idea is we kind of want to be able to pick off these exponents or these properties of how these exponents are affecting our function x one by one. So when we have this quantity x to the 2/3 all raised to the -1, that's, if we apply this -1 exponent, that's going to be our reciprocal. So we're going to have 1 divided by our x to the 2/3. So we're applying this reciprocal property. And then x to the 2/3 we can also now write as 1 over the cube root of x squared. So all of these functions, or all these descriptions of this function, are the same. Building upon this, we next talk about rational functions. These are going to be functions of the form p of x over q of x, where p of x and q of x are polynomials. So nicer in some ways than the last example, we're not going to have roots, or we're not going to have crazy exponents. All the exponents now are going to be integers in both the numerator and denominator, but we can add and subtract different powers. So for example, The basic one we started with, 1 over x, that's going to be a polynomial. But we can come up with more complicated examples as well. So any polynomial x squared minus 2x plus 1 over something like x minus 1, going to be a polynomial, or excuse me, a rational function, since both the numerator and denominator are polynomials. And then, again, our polynomial examples could be a little more complicated. So anything like that, also a rational function. The coefficients do not need to be integers. So that's kind of the typical order of building up to the complexity of our functions. The last group of functions, I guess it kind of branches, some depending on the schools of thought. In the math department, we typically go into exponential and logarithmic functions after rational functions. But in this class, it looks like we're going to go into trig functions. So it's just kind of like back and forth as to what you think is more complex. I've had semesters where a lot of students think logarithms are a lot more difficult than trig. Other semesters, students find trig a lot more difficult than logs and exponents. So our trig functions, we went over on Monday and Tuesday, or Monday and Wednesday. And so we have sine of x, cosine of x, tangent of x, cosecant of x, secant of x, and cotangent of x. I do like to keep them in this order. These are going to be the 3 main ones, and even more narrow, I guess, if you want to think. The sine and cosine are really the foundational building blocks of all the other trig functions. Tangent you can think of as sine divided by cosine. And then these 3 trig functions will be useful for the sake of calculus, but in terms of building up the main foundational understanding of trig, they are just the reciprocals of the ones listed to the left of them. So the reciprocal of sine, 1 divided by sine gives us cosine, 1 divided by cosine gives us secant. Excuse me, 1 divided by sine gives us cosecant, 1 divided by cosine gives us secant, 1 divided by tangent gives us cotangent. So always be careful with that. Students will commonly confuse where the co goes with. Just remember it's the opposite of what you would think. So cosine, when we take the reciprocal, is just secant, whereas sine, when we take the reciprocal, gives us the cosecant. We then have exponential functions. I guess I should mention there are inverse trig functions. Hopefully you guys have been exposed to, and they're also hyperbolic trig functions. I'm not sure if you guys cover that in pre-calc. We'll cover those both later this semester. So we don't expect you to know too much of the inverse trig functions. And I don't think we require a lot of hyperbolic trig functions. Those will be covered later this semester and play a role throughout the rest of calculus. Exponential functions, though, are going to be functions of the form f of x is a lot of different models for this. Let's say a times b to the x. Common variables used. In applications, you'll see all sorts of different types of variables. You often see something like a of x is something like a naught e to the kx, or sometimes x is t. So this might be an accrual of an annuity. Sometimes we have population functions where p of x is equal to p naught e to the kx. So in population growth, we'll use exponential functions a lot. In half-life, radioactive decay, depending on what letters you use, We often like to use A again. Sometimes it's C. So A of t is going to be our A naught. Base is often something like 1/2 to the t over lambda, where lambda is going to be the half-life of a certain substance. The inverse of exponential functions are going to be our logarithmic functions. So this is going to be f of x is equal to log base b of x. So note that if we have y is equal to log base b of x, then this is the same as b to the y equals x. So hopefully this is all familiar from pre-calc, that the base of the logarithm and the base of the exponent are always going to be the same in the equivalent expressions of logarithmic versus exponential. So here in our exponential functions, we call b the base of the log. This a is typically referred to as the starting value or the initial value. So for something like an accrual, it might be the initial amount we invest. This e now is our base. This k might be a certain factor regarding the rate of return, and can be thought of similarly as in regards to population growth. So population growth, this k is going to be related to the rate of the population growth. And then similarly, if you want to play some games with the exponential algebra here we have a base of 1/2, and then this factor of lambda that we're dividing by regards the half-life. So on the flip side, on the reciprocal side, or excuse me, not the reciprocal, on the inverse side, we have the base of the logarithm. So the base of the logarithm determines the growth rate of the logarithm. So logarithms are a very slow growing function. And so think of it as just taking the inverse of our exponential function. So see me in office hours or after class if you want to discuss more, some of the properties, especially the properties of logs, all the sum formulas. The product inside of a log determines a sum outside of a log, all that kind of stuff. Hopefully it's familiar from pre-calc. Some of the key things I guess we should point out, since we have a little bit of time, that the domain for exponential functions is -infinity to infinity, whereas the range is, round bracket 0 to infinity. So it's a horizontal asymptote at 0. As long as we're not shifting anything up or down, range is going to be 0 to infinity. When we create inverse functions, those are going to flip. So our domain for logarithms is 0 to infinity, and the range is -infinity to infinity. So just a word on that in terms of finding the domains. We didn't do any examples. We haven't had time for it. The domain of a function in general for this class and I'm going to say if not given. So if we give you a specific domain, it's going to restrict that function only over those specific set of x values, a specific set of inputs. If it's not given, it's assumed to be all real numbers except where undefined. And what do I mean by undefined? we now have essentially all of the operations we cannot do. So undefined is usually just we cannot perform a certain mathematical operation. So the first thing we saw was square roots. So when we're looking at these power functions, what can we not do? We cannot take an even root of negative numbers. Meaning if my function is square root of x, then our domain, what can we not do? We cannot plug in negative numbers. We can plug in 0. 0 is fine. But all the numbers we plug in have to be 0 or bigger. So our domain is going to be 0 to infinity. We cannot divide by 0. So in our rational numbers, or excuse me, our rational functions, we cannot have q of x be 0. In other words, q of x has to be non-zero. So typically finding the domain of a rational function, we set the denominator equal to 0, and wherever we find those zeros, we throw those out of the domain. And then our last one that we just saw, we cannot take a log of 0 or negative numbers. So if we have f of x log base b of x, doesn't matter what the base is. Again, our domain is going to be open bracket at 0 to infinity. So it has to be bigger than 0. Those are essentially all of the domain restrictions that we're going to have at the moment up until we get to inverse trig functions. Those will be restricted as well. Okay. So things we need to talk about are transformations, combinations, should say piecewise functions.
It's lagging again.
Okay, so next subset of topics we want to talk about: transformations, combinations, piecewise functions. I might start commonly abbreviating functions FNCTS. And then some other concepts maybe we'll get to: symmetry in terms of even and odd functions, and increasing and decreasing.
Professor Belcher, it's still not working.
Still
It's
lagging?
lagging. We can't really see your thing.
Bummer.
It's just really blurry.
Okay. So last topics: transformations, combinations, piecewise functions. Maybe we want to touch on even, odd, and increasing and decreasing functions. So only have about 5 minutes. Transformations, hopefully you guys covered in pre-calc. We want to be able to make new functions out of all the functions listed above. So transformations, we have our y transformations are going to be things like CF of x, and f of x plus c. So this is going to correspond to a stretch or compression of our y-axis, or of our y values of the function. So if c is a fraction, it's going to shrink it. If c is a whole number or bigger than 1, I guess I should say, it's going to stretch it vertically. If we add c, this is going to be a shift up by c. If c is negative, corresponds to a shift down. Our horizontal transformations are going to be f of cx and f of x plus c. This is going to be a horizontal compression or a stretch. So remember that transformations on the x direction are opposite of the y. So think of it as a pre-transformation, really what's going on. Whereas these transformations are transformations that happen after the function. So we're transforming the functional values. Whereas these transformations, in some sense, they're transforming the input first, and then we're applying the function. In other words, they're transforming the space we're acting on from the function. So it kind of inverses the values or the operations. So in some sense here, if c is bigger than 1, it's going to stretch things. So if c was 2, it's going to stretch the graph of the function vertically and stretch everything by a factor of 2. Whereas here, if c is 2, it's going to compress everything by a factor of 2. So it's like the opposite. And if c is, say, a half, here it's actually going to stretch horizontally by a factor of 2. And likewise, this f of x plus c, so careful with this plus here. This is going to be actually, let's be careful. Let's say minus. Typically in the book and in our typical pre-calc courses, we have f of x minus c, or f of quantity x minus c. This is a horizontal shift to the right. And so we specifically emphasize that minus sign. So if c is positive, the overall expression will be negative. So if it was x minus 2, that's a shift to the right by 2. If it's x plus 2, that's a shift to the left by 2. The last thing to mention, I'm just going to squeeze it in here, is that we're going to get flips if this factor is negative. So in other words, if our c value, if the product of the thing we're multiplying by is negative, it's going to flip it. If it's negative outside of the function, flip vertically. So it's flipping all the y values. If we have f of negative x, it's going to be a horizontal flip. So in that regard, that's going to be our even and odd functions. Even functions means that if I apply a horizontal flip, I get the same function. Odd functions are functions where if I apply a horizontal flip, it's actually the same as applying a vertical flip. Odd functions, we say, are symmetric about the origin, meaning if I flip across the x-axis and then flip across the y-axis, we get the same thing. Even functions, if I just flip across the y-axis, we get the same function. So combinations of functions. The other ways we get new functions is new functions and operations with other functions. So we can always add two functions. We can multiply and divide two functions. So commonly we write this as f plus g. of x. We write this as f times g of x. Likewise, f divided by g of x just means we take the y values and divide them. And then on functions, we have an extra operation, and that is composition. F composed g of x means apply all of the operations of g to the input, take that output, and then apply the operations of f. So composition of functions, again, if we want to think of functions as a sequence of mathematical operations, composition just says perform all the sequence of operations on whatever input. So perform all the operations of g first, then take that output and keep performing the operations of f. So those will play a big role this semester, especially with some of the derivation rules that are going to come up. Okay, let's see. Anything else? I think we're about out of time. So let's go ahead and end it there.